Hey there, it's Shannon Matchick-Myers. Today we'll be looking at section 7.4.2 from the ZIL Intro to Differential Equations text and covering transforms of integrals. So this is a continuation of our chapter on Laplace transforms. Convolution. If functions f and g are piecewise continuous on the interval from 0 inclusive to infinity, then the convolution of f and g, which is denoted by a star symbol in between them, so f star g, is a function defined by the integral. So the convolution of f and g is equal to the integral from 0 to t of f at tau, that's the Greek letter tau, times g at t minus tau with respect to tau. Since we are integrating with respect to the variable tau, which is the lowercase Greek letter spelled T-A-U, tau, the convolution of f and g is a function of time, of t. So to emphasize this fact, we also sometimes write the convolution of f and g as f star g at time t. The convolution is often interpreted as a generalized product of two functions, f and g. Okay, so let's take a look at example 1, where we're going to find the convolution of f and g of the given functions below. After integrating, we find the Laplace transform of the convolution of f and g. So here we go. The convolution of f and g is going to equal to the integral from 0 to t of f at tau, right? So since f at t is t, f of tau is just going to be tau. Now be careful, because wherever you see a t in g at t, we're going to replace this one with t minus tau. So we have g at t is e to the negative t, so g at t minus tau is going to be e to the negative quantity t minus tau. And it's with respect to d tau. Cool so far? All right, so this one we're going to need to do a quick integration by parts. And so before we do that, let's go ahead and simplify this just a little bit. So this convolution of f and g is going to be equal to the integral from 0 to t of tau. Now, this would end up being e to the negative t and then plus tau, right? If I bring that minus sign in, and then I still have my d tau, but I can also rewrite this as tau times e to the tau, and then can't I factor out the e to the negative t, because I'm differentiating with respect to tau. So that's going to make it easier to do the integration by parts. It'll be relatively simple. So here u would equal to tau, du is just equal to d tau, and then dv will equal to e to the tau d tau, so v is equal to e to the tau. Cool? So my integral of tau e to the tau d tau will be equal to u times v minus the integral of v du. So that's going to be u times v will be tau e to the tau minus the integral of v du. We'll have e to the tau d tau. So we'll get tau e to the tau minus e to the tau. Groovy? Okay. So we'll put that over there. So now, when I go through here, I'm going to end up with e to the negative t times, and then we'll have, I'll write it as e to the tau times tau minus 1. And that's going to be evaluated from tau is 0 to tau is t. And this will give us e to the negative t times. My upper limit of integration will be e to the t times t minus 1 minus my lower limit of integration, which will be e to the 0 times 0 minus 1. So when I multiply that e to the negative t through, now remember this over here is just going to be a positive 1, a plus 1 because of the two negatives. So I'll get e to the 0 for the first term, so then I'll just be left with t minus 1, and then e to the negative t times positive 1 is e to the negative t. So what I found here was the convolution. So this here is the convolution of f and g. All right? But we also need to find our Laplace transform. So L of the Laplace transform of the convolution of f and g is equal to the Laplace transform of t minus 1 plus e to the negative t. And remember that your Laplace transform is a linear operator, so I can take it to each one of these terms and apply the transformation. And you can either look at your chart, to find these. Hopefully you've done enough where you probably remember these guys. 1 over s squared will be this first result. And then minus 1 over s is our second result. And then for this one, our a in this case is negative 1. So we'll have plus 1 over s minus negative 1. And that's because of the coefficient to that e is negative 1. And then we'll get a final result. Well, let's get a common denominator. So we'll end up having, you see our common denominator will be s squared times s plus 1. And so we'll have 1 times s plus 1 minus 1 times s plus 1. And then the last one is just missing the s squared. And simplifying this, what will we have? 1s plus 1 minus s squared minus s plus s squared. So at the end of the day, we actually, believe it or not, just get 1 over s squared times s plus 1. Cool, cool? All right, and so that takes care of the Laplace transform of the convolution of f and g. Groovy? Okay, so the convolution theorem, which is theorem 7.42, if f at t and g at t are piecewise continuous on 0 to infinity, including 0, and of exponential order, then it turns out that the Laplace transform of the convolution is equal to the product of the Laplace transforms, which is really awesome. Which, of course, if you write it this way, would be capital F at S times capital G at S. So let's take a look. If we let capital F at S equal to L at F at T, which, if we write this in terms of the definition, we'd have the integral from 0 to infinity of e to the negative s tau times f at tau d tau. And we'll let g at s equal to L at lower g at t, which is equal to the integral from 0 to infinity of e to the negative s beta. We'll use beta instead of tau. Times g at beta d beta. So now we want to multiply. We want to see what the product looks like. So capital F at S times capital G at S, which are the results of the Laplace transforms, is going to be equal to the integral from 0 to infinity of e to the negative s tau times f at tau d tau times the integral from 0 to infinity of e to the negative s beta times g at beta d beta. So now this is going to be equivalent to the double integral from 0 to infinity on each of them of e to the negative s. So if I were to multiply e to the negative s tau times e to the negative s beta, I can factor out a negative s and I'd be left with tau plus beta. See that there? And then we'll have times f at tau times g at beta d tau d beta. But that in turn is equal to the integral from 0 to infinity. Now, if I'm just looking at integrating with respect to beta, I can do a little trick here. I can take out the f at tau d tau, and then I'll have the integral from 0 to infinity of e to the negative s times tau plus beta times g at beta d beta. So here we're going to now take a look. We're going to let tau be fixed. And t be equal to tau plus beta, which of course gives us that dt would be equal to d beta. So with that little switcheroo, we'll end up having the integral from 0 to infinity of f at tau d tau, that's not going to change, times the integral from 0 to infinity of e to the negative st, because remember t is equal to tau plus beta, and then g is going to be at t minus tau dt. So here's what's going on if we're looking at the t tau plane, right? So we've made a switch, right? If this is our tau axis and this is our t axis, and if for tau equal to some t, for tau equal to t, you'd have, this graph here. And then if you look at the area under the curve, right? We'll just take a look here. It would just keep going on in that manner. So tau is moving vertically, right? So this right here would represent tau moving from 0 to t, right? And then going this way in the horizontal. So going horizontally, you'd start at t equal to tau, right? And then t would keep going on to infinity, right? So this is what's happening with t. So that means we can change this up a bit, and we can say that this is the integral as we go from 0 to infinity of e to the negative st dt, right? And then the integral from 0 to t of f at tau times g at t minus tau dt. But what is that? Perfect. That's the convolution of f and g, right? And so this is equivalent to L of the convolution, the Laplace transform of the convolution of f and g. Groovy? Okay. So, example 2. Find the Laplace transform of the convolution of f and g using theorem 7.4.2, and don't use the convolution integral before transforming. So, here we go. We've got the convolution of e to the 2t and sine at t, and we want to find the Laplace transform. So remember that we're allowed to do what? Beautiful. Multiply. So this would be the Laplace transform of e to the 2t times the Laplace transform of sine at t, which is the coefficient of the e is 2, which is positive. So the first transform will be 1 over s minus 2. And so that's this whole thing is this. And then the second one will be the Laplace transform of the sine function is the coefficient to the t, which is 1, right, over s squared plus the coefficient of t squared, which will just be 1 squared. And that is this whole second one. So then we'll just get 1 over s minus 2 times s squared plus 1. And we're done. All right, so now this next one, there's a little bit of a trick to this one. So here we've got this integral of something that almost looks like a convolution. It sort of looks like some stuff we learned in the last section because of that tau sine tau, right? So here, one thing we can do is this. We can say that if g at t is 1, right? It's like the horizontal line, y is 1. Wouldn't g at t minus tau also be 1? So there's this little kind of trick we can use where we have this 1 in there in the transform. Okay, so what will happen is this. We'll end up getting the Laplace transform of t times sine at t times the Laplace transform of 1. We'll go into a little more detail on this soon. And so that's going to give us, for the first one, remember, we know the Laplace transform of sine at t. So we would have negative 1 to the 1 times the first derivative with respect to s of this Laplace transform of sine at t times the Laplace transform of 1, which is 1 over s. So that's going to give us a negative. I'll bring the 1 over s up front, and then we'll have the first derivative with respect to s of this Laplace transform, which will be k, which is 1, because the coefficient of the angle is 1, and then s squared plus 1 squared, which of course is just 1. And so that is our Laplace transform of just sine at t, but we have to integrate it, or not integrate, differentiate it. So we'll have negative 1 over s times, well, this will be, using the chain rule, negative 2s over s squared plus 1 squared. And so at the end of the day, the s's will divide out. The negatives will go to positive, and we will have 2 over s squared plus 1, the quantity squared. Cool, cool? Okay, so now let's take a look at some other cool stuff. The inverse form of that last theorem. All right, so the convolution theorem is sometimes useful in finding the inverse Laplace transform of the product of two Laplace transforms, right? So many of the results of Laplace transforms in Appendix C of our text, or you could probably search for online for Laplace transforms, can be derived using the following equation. So the inverse of the Laplace transform for capital F at S times capital G at S is equal to the convolution of F and G. And remember, you've got your convolution definition here. So all we did here is we inversed this part, right, and this part. Cool, cool? Okay, so the transform of an integral. When g at t equals 1, that little trick we used last time, and L at g at t would equal to capital G at S, which is equal to 1 over S, the convolution theorem implies that the Laplace transform of the integral of F is the Laplace transform of the integral from 0 to t of F at tau d tau. Which will equal to, so that's the Laplace transform of that integral, okay, is going to equal to the Laplace transform of F over S, because of that 1 over S that you get from letting g at t equal to 1. So the inverse form of this equation would, of course, be the integral from 0 to t of f at tau d tau is equal to the inverse of that Laplace transform of f at S over S. Cool, cool? And so that's exactly what we did on this one, right? We took that t times sine at t as our f at t, and that's how that worked. All right. So this inverse form can be used instead of partial fractions when s to the n is a factor of the denominator and f at t equal to L inverse at capital F at S is easy to integrate. You want it to be easy to integrate. You don't want to make more work for yourself. So let's take a look at something we've been using quite a bit. If we think about let's say our f at t is sine at t. And so that means that capital F at S is what? What's the Laplace transform? Beautiful. Your k is 1. So you have k over s squared plus k squared. And k squared is 1, so you just get 1. Cool? All right, so now we can utilize this to find some other cool stuff. We did one of these already. So if we take a look at L inverse of 1 over s times s squared plus 1, then you would want to think about that as L inverse of. You'd think about it as the 1 over s squared plus 1, right, that we have from our, that we know is a Laplace transform result for sine at t. And then you put that over the s. So we're just creatively rewriting that fraction, messing it up a little bit. And now what this last thing said is that it's going to equal to the integral from 0 to t of sine at tau, because that's our Laplace transform, right? Our inverse Laplace transform of 1 over s squared plus 1 is sine at t. Well, we're integrating, or we have t in the integral, so we're putting the dummy variable tau in there, d tau. And that in turn is what? What's the integral of the sine function? Beautiful. Negative the cosine function at tau, and tau is going from 0 to t. So what do we get? We would get negative cosine at t minus a minus cosine at 0, which gives us a positive 1. So I'll write it prettier as 1 minus cosine at t. And that's what you would have for that. So it's actually pretty useful. So let's take a look at another level of it. So if we're looking at the inverse Laplace transform for 1 over s squared times s squared plus 1, well, what do? We look at what we found from this last one, which is 1 over s times s squared plus 1, that whole thing in that denominator, over s. So that would end up being the integral from 0 to t of our last result, which is 1 minus cosine, putting in tau, and then d tau, which will be equal to tau. So the integral of cosine at tau is sine at tau, right? So you'll get minus sine at tau. Evaluated, tau goes from 0 to t. Sine at 0 is 0. So you're just going to get, and when you plug in 0 for tau, you'll get 0. So this one will just be t minus sine at t. And then we'll do one more. Let's say we're finding the inverse Laplace of 1 over s cubed times s squared plus 1. Well, that's going to be what we found last time over s, which is the integral from 0 to t of tau minus sine at tau with respect to tau. That's going to be tau squared over 2. The integral of the sine function is minus the cosine function, so we'll have a plus cosine at tau. And tau is going from 0 to t. So that's going to give us what? T squared over 2 plus cosine t. And then we'll end up with the 0, we'd end up minus 0 plus 1. So we'll have a negative 1. So this would be cosine at t. Actually, sorry. This is going to be, I'll write it down here, equal to t squared over 2 plus cosine at t minus 1. Groovy? Okay, so now let's take a look at example 3. So we're going to use this integral here to evaluate our inverse function. So we want to write this as L inverse of one over s minus a squared over s. So this is one of those times where you might need to go and look at your Laplace transforms. There's a couple ways you can look at this one, right? The ideal way would be for you to recognize that. So, evil plan. If you have this here, right? Wouldn't that just equal to t, the Laplace transform? The inverse, Laplace transform of 1 over s squared is equal to t, correct? Now, what's happened to s? It's been shifted a units to the right. And so here, you'd be looking at the inverse Laplace transform for this 1 over s squared, where s is approaching s minus a, right? And so that ends up being what? You'll get your t from the 1 over s squared, but to represent that shift of a units, you'll have e to the a t. Cool. And so here's the beauty of it. We know that transform now, and that's not a hard integral to do. So this will end up being equal to the integral from 0 to t of tau e to the a tau d tau. So that was the first part of our evil plan. You can also look at the table of the Laplace transforms if you spaced out on that. Second part of evil plan is integration by parts, right? So if u is tau, du is d tau, dv is going to be e to the a tau, d tau, and so v is 1 over a e to the a tau. Cool so far? Okay. So the integral of tau e to the a tau d tau will be u times v. So tau times 1 over a e to the a tau minus 1 over a integral e to the a tau d tau, which will end up being 1 over a tau e to the a tau minus 1 over a squared e to the a tau. And let's pretty it up a little bit. 1 over a squared, we would have a times tau times e to the a tau minus e to the a tau. And now we are going to have to go over and evaluate it, right? So this will be equal to, we can actually take out the 1 over a squared and then put in our result that we got over here. A times tau times e to the a tau minus e to the a tau. That's going to be evaluated from tau is 0 to tau is t. So we will get 1 over a squared of a t e to the a t minus e to the a t for our upper limit And then lower limit will be 0 minus e to the 0. So at the end of the day, we will have 1 over a squared times at e to the at minus e to the at plus 1. And we're all done. Pretty groovy, huh? All right, so next up, we're going to check out the, we didn't need all those pages, I guess. We're going to check out the Volterra integral equation. So the convolution theorem and the result where we have the Laplace transform of the integral from 0 to t f at tau d tau equal that whole transform equal to capital F at S over S are useful in solving other types of equations in which an unknown function appears under an integral sign. So you might have some f at t equal to g at t plus the integral from 0 to t of f at tau times h at t minus tau d tau, where we know h and we know g, but we don't know f. So let's take a look at how we would use that. So we're going to use the Laplace transform to solve the given integral equation or integral differential equation. So this first one's an integral equation. We have f at t equals 2t minus 4 times the integral 0 to t sine at tau f at t minus tau with respect to tau. Cool? So here we go. We're going to take the Laplace transform of the whole thing. So Laplace transform of f as what it is on the left side, and then remember it's the Laplace transform is a linear operator, so we'll have the Laplace transform of 2t minus 4 times the Laplace transform of the integral from 0 to t of sine at tau times f at t minus tau d tau. So in here, this is the convolution of sine at tau and f at tau, right? So if you look here at the theorem, way back here, remember we're allowed to, the convolution, first of all, is this. Look familiar? Right? Except we have G and H instead or something like that. So that is the convolution of f and g, right? And it turns out that the linear transform of a convolution of f and g is the product, right, when they're evaluated at t. So coming back, we can rewrite this whole last thing here as minus 4 times L at sine at t times L at f. And then this one over here is going to be 2 times L at t. And then we have another L at f over here. So if I add this whole expression to both sides, I will have 4 times L at sine at t times L at f plus L at f will just be equal to 2 times L at t, which will be 2 times 1 over s squared, because L at t is 1 over s squared. Cool, cool? And now let's take a look at what's happening over here. So we'd have 4 times the Laplace transform for sine at t. We've got a sine at 1 times t, so k is 1. So we'll have 1 over s squared plus 1 squared, so s squared plus 1. And then we have this L at f, and then we have plus another L at f. So what if I went ahead and said plus 1, factored out the L at f on the right, and then that's equal to 2 over s squared. Cool so far? On the left side, let's clean this up a little bit. We will have 4 plus s squared plus 1 all over s squared plus 1, just getting a common denominator, times L at f equals 2 over s squared. And then isolating my L at f, I will have 2 over s squared times the reciprocal. So I'll have an s squared plus 1 in the numerator over s squared plus 5. Cool so far? All right, so now let's just take a look at what we have going on. That's where I needed my extra page, I know now. So we're going to work with this here, and what the heck, we're going to do a partial fraction decomposition on it. So we have this going on. So now when we do our partial fraction decomposition, let's see what we get. We're going to have 2s squared plus 2 over s squared times s squared plus 5 equals a over s plus b over s squared plus c s plus e over s squared plus 5, because that's an irreducible quadratic. And then getting a common denominator on that right hand side, we'll have 2s squared plus 2 equals a times s squared plus 5 plus b's only missing the s squared plus the 5, and then we'll have plus cs plus e is missing the s squared. So we'll have 2s squared plus 2 equals as cubed plus 5as plus bs squared plus 5b plus cs cubed plus es squared. So we'll have a 2s squared. We have 0 s's, and then we have a constant 2. That's going to equal 2. So I have how many cubed terms? Just 2. I have a plus c times s cubed. And then s terms I have or s squared terms rather, I have b plus e s squared. And then s terms, I have 5a. And that's it, I believe. And then constant terms, I just have plus 5b. Cool so far? All right. So now, here we go. Remember that you equate coefficients. So I don't have a cubic term, so I should have written that in. 0s cubed. And so I'm going to equate the a plus c to the 0, the b plus e to 2, 5a to 0, and 5b to 2. And I will have a plus c is 0, b plus e is 2, 5a is 0, and 5b is 2. So from that system, b has to be 2/5, right? A has to be 0, which would make c equal to 0 as well. And then e would be equal to 10/5, getting a common denominator, minus 2/5, which is 8/5. Cool so far? So at the end of the day, 2s squared plus 2 over s squared times s squared plus 5 is going to equal to, remember a was zeroed out, so 0 over s is just 0. And b, we'll have b over s squared. So we have 2/5 times 1 over s squared. C zeroed out, so e was the constant part of that one. So we'll have plus 8/5 times 1 over s squared plus 5. All right, so now that that is all done, joy, joy, we can continue. So L at F will be equal to 2/5 times 1 over s squared plus 8/5 times 1 over s squared plus 5, which looks kind of like something we could make into a sine function, right? So let's do that. If I multiply this by root 5, do you see that root 5 squared is 5? But we're also going to have to adapt because we want to multiply by 1. So when we finish, we need to find the inverse Laplace transform of L at F is going to be the inverse Laplace transform of 2/5 times 1 over s squared plus 8 over 5 root 5 times root 5 over s squared plus root 5 squared. So this, of course, will just be f at t is equal to, we're going to have 2/5 times t plus 8 over 5 root 5 times sine at root 5 times t. And we're done. Cool, cool? Okay, so next up, another example. For this one, where you're going to solve this. This one would be an integral differential because it's got a derivative in there. So we'll just call that y prime. All right, so applying our Laplace transform to both sides, we'll have L at y prime plus 6 times L at y plus 9 times L at integral 0 to t. We're going to use that trick, so we have y at tau, and we're going to have times 1, so we're going to let g at t equal 1 d tau, and then that'll be the Laplace transform of 1. So here we go. This is going to end up being y at y at s minus y at 0 plus 6 times y at s plus 9 times L at y times L at 1 is equal to 1 over s. Remember, L at y prime is equal to this. L at y was equal to capital Y at s. And then all of this stuff is this. Groovy? Okay, so continuing. Remember that y at 0 is 0. So we will have s times y at s plus 6 times y at s plus 9 times y at s times 1 over s equals 1 over s. Factoring out a y at s to the right, we'll have s plus 6 plus 9 over s. Y at s is equal to 1 over s. And now I'll go ahead and clean this one up a little bit on the left side. So we'll end up with, we need a common denominator of s, so we will have s squared plus 6s plus 9 all over s times y at s equals 1 over s. And then isolating y at s, we will have 1 over s times the reciprocal, which would be s over s squared plus 6s plus 9. The s's will divide out to be 1, and we'll get y at s is equal to, so we'll have 1 over, do you guys see that that is s plus 3, the quantity squared in the denominator? And so now, what can we do with this? So if we look at our handy dandy list of formulas, right? Remember, we're going to find the inverse transform so we can solve this. I'll write this out as s minus negative 3. That quantity is squared. So if we go to our table, and you might remember it from something we've seen before, but if we go to our table, you will see 1 over s minus a squared. That quantity squared is te to the at. So I'm looking at this guy here, number 16. So my a in this case is negative 3, right? So then we'll come back over and we'll say y at t is equal to te to then a, which is negative 3t. And we're all done. And that was formula number 6 on or in Appendix C. Cool, cool? All right, and we're all set. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, please hit the like button for the video and subscribe to my channel. Thanks, bye.